3.10, derivatives of inverse trig functions. We can see from our picture here that if we had the original sine function, which would be my pink curve here, would be something like this. And then if we want to go ahead and find its inverse, remember we are switching its domain and range. I get more of this blue shape of the function, but if I was to keep going with the curve, I would no longer pass the vertical line test and I can no longer call myself a function. So we restrict the pieces that we can take for our domain and range of the inverse sine function. So notice, remember, if our x and y values are switching, our domain and range are switching for inverse functions. So now the domain of the sine inverse is -1 to 1, and the range is -π/2 to π/2. So I have this original function and I want to find its derivative. So basically, if I can remember what we do when we do inverse functions, we switch the x and y's and try to solve for y. So if I have here where I switch the x and y and I solve for y, I say, okay, sine inverse of x. But if I go back to what I originally had here, sine y equals x, and then I'm going to take, this is its inverse, I'm going to take its derivative because I don't know yet how to take the derivative of sine inverse, but I can take the derivative of sine. So I'm going to go ahead and take the derivative of both sides. And I see my left-hand side is 1, and my right-hand side will be cosine y, but because it's with respect to x, I have to do the chain rule and saying times dy dx. I'm then going to solve this for dy dx, and I see that it's 1 over cosine y. But that's not in terms of x. So I'm going to use some kind of properties in order to do some substitution. I'm going to go back to the Pythagorean identity, cosine, and in this case I'm going to say y, cosine squared plus sine squared is equal to 1. So I want to go ahead and solve for cosine y so I can substitute that back in. When I solve for cosine y, I should get the square root, a positive and negative square root of 1 minus sine squared y. But that still is in terms of y. But if I go back to my original back up here and square both sides, I see then that if I have x squared is equal to sine y squared, I can replace this with x squared. So then I'm going to say, okay, I'm going to go back to my original function here, dy dx, and replace my cosine y with the square root of 1 minus x squared. But I originally had a positive and negative square root. But because of the restrictions, I'm going to only have the positive branch of this inverse function. So from here, I now have my derivative for sine inverse. So if I can go to my theorem box here, I say the derivative of sine inverse of x is 1 over the positive square root of 1 minus x squared, noticing the restrictions, -1 to 1. Let's go ahead and do some examples. We're going to do number 7, which number 7 says, given the function f of x is equal to sine inverse of 2x. All right, so then I'm going to say the derivative. The parent form of this derivative is 1 over the square root of 1 minus x squared, but I don't have just an x squared situation happening. Remember, it's not just sine inverse of x, it's sine inverse of 2x. So then I also have to do the chain rule. The derivative of my inside 2x would be means I have to multiply by 2. So simplifying this, I have 2 over the square root of 1 minus 4x squared. And there's my answer. We're going to do now number 12, which says given this function f of x is equal to the sine inverse of e to the sine x, and I want to find this derivative. So if I go ahead, do the same process, my parent function form of this inverse should be 1 over the square root of 1 minus x squared. But I have, instead of x, e to the sine x. Then I also notice I have to take the derivative of the inside function. So I'm going to multiply by times e to the sine x. But then remember, it's not just e to the x. I have to take the derivative of sine x, which would be cosine x. Going and simplifying this expression, I'll have cosine x times e to the sine x over the quantity, the square root of 1 minus e to the 2 sine x. I now look at my graph here for tangent. I have the domain of tangent inverse, and the range of tangent inverse. Notice though, remember, our range is now not restricted, but our range is now restricted. Remember, the domain and range switch, and I have these graphs. If I was to go through the same process of trying to prove this inverse, we would go through the same steps, but you can follow this in your book on page 223 to 224, and also for secant and cosecant. Remember, secant and cosecant graphs are definitely restricted. Remember, we would have graphs such as this, and then our inverses are a special case. So we have a lot of restrictions going on with those. But long story short, we have that our 6 trig inverse functions have these derivatives. Remember, our shortcut for if it's a tangent, if it's a trig inverse that begins with a c, we have a negative version of our derivative. Then let's go on to some examples. Given the function of just tangent inverse of 10x, we can see then that its derivative and its parent function form is 1 over the quantity of 1 plus x squared. But remember, we don't have just x. So I'm really going to have the 10x squared. So I'm going to have to go ahead and multiply this by its chain rule of the inside function, and then 1 plus, and we have this situation. Our book does put this in this position where the 100x squared is first, and then the plus 1. If we move on to another example, number 17. Cotangent inverse of z, the square root of z. I'm going to go ahead and rewrite this as the cotangent inverse of z to the 1/2. So then if I want to go ahead and take this derivative, I have that because it's cotangent, I know it's going to be a -1 over, and it turns out that it should be 1 plus x squared. But in this case, I want to make sure I don't have just the x. I'm going to have my special case where it's z to the 1/2. And then I'm going to have to multiply by the derivative of z to the 1/2, which should be then 1 over 2 times the square root of z. So if I go ahead and simplify this expression, I have a -1 over 2 times the square root of z times the quantity of 1 plus z. And this is my final derivative. Let's do one more on this section. We'll do number 26. If I'm given the function tangent inverse of e to the 4x, let's find this derivative. Remember, this will be 1 over 1 plus x squared, but we're not really doing x squared. We're going to be doing e to the 4x. And then if you remember, then from here, I have to do the derivative of the inside function. And then I have to remember it's not just e to the x. I have to do another chain rule of e's exponent. So I now have 4e to the 4x over 1 plus e to the 8x. And there's our derivative. All right, so from here, I want to talk about inverse functions. Let's review a little bit of how to find an inverse function. So for example, if I'm given that a function is 4x plus 3, we want to go ahead and find its inverse. We switch the x and y, so I have x equals 4y plus 3, and I'm solved for y. And then instead of saying y, I have to rename this new function when we say the inverse function. So then I have here, this is basically a linear equation, and I found its inverse. My original equation had a slope of 4. If I was to take the derivative of that, it would be 4. In this new inverse function, I can see, well, this, if I took the derivative of this new function, it would have a slope of 1/4. So for this case, we can see in generic terms, we can say y would equal, for the inverse of it, 1 over mx minus our intercept in this form. So then that becomes very easier. Instead of just saying m, it becomes the derivative of it is 1 over m. So if our domains and range switch, we can go through the proof on page 228 for all inverse function, but it turns out the derivative of inverse function at a certain point, we could say the derivative of the inverse function in respect to y is really 1 over the derivative with respect to x. So then let's go ahead and try to walk through a couple of examples of these. We're going to do number 37. I'm given the function f of x equals 3x plus 4, and I'm going to want to evaluate it at the point 16,4. But I want to just say, using our derivative of the inverse, I'm going to take the derivative of this function. So I'm going to say it's really this. And then just say the derivative of 1 over the derivative of this would be 1/3. There is no x to evaluate at the point 16,4, so our answer for this one is 1/3. Let's do another example, number 41. I'm going to be given this function, tangent x, and I want to evaluate it at the point 1 pi over 4. So then from here, I can see that the inverse derivative, sorry, this should be y, should be 1 over the inverse of x, which will be 1, the derivative of tangent is secant squared. But I'm going to evaluate it with respect to the y. So this is what I need to say. So from here, I'm going to say the inverse function's derivative of pi over 4. Remember what secant of pi over 4 is? It's the square root of 2, and it's going to be squared. So I really have the answer of 1/2. All right, so moving on, I want to do some more examples. Let's go ahead and do an example 31. Given this function, let's evaluate it at this point. And then let's find the equation of the tangent line. So if I want to go ahead and find the derivative of this function, remember our parent function form of this one is 1 over 1 plus x squared. Our x is going to be 2x though, and then following the chain rule, I'm going to multiply by 2. So I now have 2 over 1 plus 4x squared. And I want to evaluate this one at this point, 1/2 pi over 4. So this is one, I did not find its inverse. This already was tangent inverse. So I took just the derivative of it. I'm going to plug in my x value to evaluate this, which would be 1/2. And when I plug in 1/2, I see that I get a slope value of 1. To find the tangent line of this, remember we're going to use the slope times and use our points in the point slope formula. Oops, that's over 4. And then if you notice though, trying to keep things exact, I really can't simplify this one by combining my pi over 4 and negative 1/2. So I'm going to leave this as the equation of my tangent line. All right, let's do another example. We're going to do example number 43. Given the function f of x equals the square root of x, and we want to evaluate the slope at the point 2, 4. So I want to find the inverse slope on this example. So I'm going to evaluate this one if I found the inverse. Well, let's see first if I put this in exponential function. I could do it that way, or I think in this case, I might find the inverse first. Let's go ahead and try that. If I did the inverse of this first, I see y would equal x squared in this case. And then if I use this to find its derivative of the inverse, I would get 2x. And because I found the inverse first, then took the derivative, I'm evaluating this with my x value. So this has a value of 4 for my slope. Okay, let's do another example, number 61. Number 61 says, here's this function. And we want to definitely set up a restriction because I know it's going to happen where x's are greater than 0. If I want to find the inverse first, I would see that I get y f of inverse. And we have this. Okay, remember our restrictions are for x is greater than 0. And then finding this one's derivative. There's times when finding the derivative of a function's inverse is easier when I do 1 over the derivative of the function, and there's times when I may want to go ahead and find the inverse first and then take its derivative. The last one I want to go through in the examples are going to be number 67, and it's an application problem. We do have in our book a picture, and this has a boat that's being winched in. And I will continue this problem in class.